Hello everyone, my name is Luay Mualem, and today I'm going to present resolving the approximability of offline and online non-monotone DR-submodular maximization over general convex sets. This is a joint work with Professor Warren Feldman from University of Haifa. Okay, so to present the problem we study in our work, we start with defining set functions. Given a ground set n, a set function f assigns a number to every subset of the ground set. One basic property of set functions is the non-negativity, which means that the function value on every subset from the ground set is at least 0. In this work, we study a DR submodular optimization problem, which is an extension of submodular function. We begin first by defining submodularity. Submodular functions have the property that the difference in the incremental value of the function that a single element makes when added to an input set decreases as the size of the input set increases. Also, submodular functions have a natural diminishing returns property, which makes them suitable for many applications. Now, formally speaking, for every two sets, A, B, such that A is a subset of B, the incremental value of the function after adding an element which is not in B to B is at most the incremental value of the function after adding the same element to A. Okay, as I previously said, we study an extension of the submodular functions, which is called DR submodular functions. It was first defined by Bayan et al. In 2017. DR submodular functions is an extension of the submodularity notion from set functions to continuous functions. Formally speaking, given a domain X, the function is called DR submodular whenever the following inequality holds. Note that this inequality is very similar to the inequality in the previous slide. In fact, this is the marginal gain property in the continuous version, which is called DR submodularity. Also, if f is continuously differentiable, the above definition of DR submodularity is equivalent to the following inequality. Furthermore, when f is twice differentiable, it is DR submodular if and only if its Hessian is non-positive at every vector x, and the comparison here is coordinate-wise. Okay, DR submodular functions have a lot of applications. For example, image summarization, text summarization, move recommendation, quadratic programming, and many more. All right, some motivation. Existing works on DR submodular optimization focused on either monotone objective functions or down-closed convex set constraints. Now, many real-world problems are naturally captured as optimization of a non-monotone DR submodular function over a constrained convex set that is not down-closed. For example, consider a streaming service that would like to produce a summary of recommended movies for a user. Often, the design of the user interface places strong bounds on the size of the summary displayed to the user, leading to a non-down-closed constraint. Furthermore, the quality of the summary is often captured by a non-monotone objective, since putting very similar films in the summary is not very good to both its value and professional look. Motivated by the previous mentioned situation, a few recent works started to consider DR submodular maximization subject to a general, not necessarily down-closed convex set constraint. In general, no constant approximation ratio can be guaranteed for this problem in sub-exponential time due to a hardness result by von Rack. However, Dar et al. Showed that this inapproximability result can be bypassed when the convex set constraint includes points whose L infinity norm is less than the maximal value of 1. Regarding the state-of-the-art for this problem, the state-of-the-art offline algorithm is a recent polynomial time 1/4 times 1 minus m approximation algorithm. However, coding this algorithm for the empirical study is somewhat non-trivial because it is presented as a part of a general mathematical framework for designing algorithms for various submodular optimization problems. M is the minimum L infinity norm for any vector in the convex set constraint K. As for the online state-of-the-art result, the approximation is as you can see here, and it takes sub-exponential time to run it. It was suggested by Thang et al. All right, so few questions remained open and gaps. First one is, what is the best approximation ratio that can be obtained by a polynomial time of an algorithm? In particular, can such an algorithm guarantee a better than quarter times 1 minus m approximation? And if not, how much slower must be an algorithm that improves this approximation ratio? The second question is there a polynomial time online algorithm guaranteeing any constant approximation ratio? Can such an algorithm match the optimal approximation ratio obtainable by an offline algorithm? In this work, we answer all the previous questions, which essentially settles the problem of maximizing DR-submodular functions over general convex sets in both offline and online settings. We start by providing the first constant approximation polynomial time algorithm for online submodular maximization over general convex sets. We also provide tight hardness results for both online and offline settings, which settles the problem. We also study the empirical performance of the theoretically optimal offline and online algorithms, showing that both algorithms consistently outperform previously suggested algorithms. Now recall that the state-of-the-art offline algorithm is a recent polynomial time 1/4 times 1 minus m approximation algorithm. However, coding the algorithm for the empirical study is somewhat non-trivial. Therefore, our empirical study is based on an explicit version of this algorithm that we give in this paper, which is not fully identical to the state-of-the-art algorithm. In this work, we present and analyze an explicit variant of the offline state-of-the-art algorithm for maximizing a non-negative DR-submodular function over a general convex set. To summarize the approximation guarantees of our variant for the offline setting, our algorithm outputs a solution obeying the following. In particular, when t is set to be ln2 over epsilon, our variant achieves the following approximation guarantee, which we prove in our work that is tight due to our inapproximability result, which settles this problem in the offline setting. As for the online setting, we provide the first polynomial running time algorithm achieving any approximation guarantee. In fact, our algorithm achieves a tight approximation guarantee of 1/4 multiplied by 1 minus m, which is the minimum norm of any vector in the convex set constraint. Let's summarize the approximation guarantees of our method for the online set. Our algorithm outputs a solution obeying the following. And again, when t is set to be ln2 over epsilon, our algorithm achieves the following approximation guarantee, which we prove in our work that is tight due to our hardness inapproximability result, which settles this problem also in the online setting. In our paper, we also study the empirical performance of our suggested methods on multiple machine learning applications. As we can see in this application, our suggested version, which is a variant of those methods, perform much better than other suggested methods. In the online setting, we can clearly see that our algorithm outperforms previous methods. It is important to note that all the algorithms have been executed for t equals 100 iterations in the offline setting and 1000 in the online setting. To demonstrate the robustness of our suggested variant in the offline setting, we also studied the empirical evaluation on a downclosed polytope. As we can clearly see, there is a big gap between the performances of our method and previous suggested methods. And this is another application on the one-line setting. Also here, we set time step to 100, and we can see that our method outperformed the previous method. Hope you enjoyed it. Please feel free to contact us. Thanks.